Hello, and welcome to another video on the series on portfolio theory. Now we're going to talk about investing in a portfolio of two risky assets. And our roadmap will be the following. We'll be first looking again at the portfolios of two risky assets. We'll be looking again at their expected return and their variance. Then we will go ahead and derive what is known as the efficient frontier. We will add a risk-free asset to the mix, and we will derive what is known as the tangency portfolio. And finally, we will look at how the correlation affects the variance, the standard deviation of a portfolio of two risky assets. So let's go at it. So if we're investing in two risky assets, and suppose that just for illustrative purposes that these two risky assets are stock and a bond, it can be anything, but let's just do it like that. And suppose that we call any portfolio of these two P. Then the return of this portfolio will be given by that expression, as we already know, where XS is the weight on the stock and XB is the weight on the bond. Now, of course, since the two weights need to add up to 1, we can write the expression of the return in terms of the weight on the stock only. Now, the expected return of one such portfolio will be given by an expression that we're now familiar enough with to derive ourselves. Now, what about the variance on the standard deviation? Once again, we can apply in a straightforward manner our formula for the variance of a portfolio of two risky assets, and that's our expression. But also, of course, since the weights once again are going to add up to 1, we can also write that variance in terms of the weight on the stock on the stock only. The standard deviation is nothing but the square root of that expression. So let's see an example. And suppose that the expected return of the stock is 14%. Suppose that the expected return of the bond is 9%. Their variances are 600 and 219 respectively. And their standard deviations are 24.5% and 14.8% respectively. Of course, the standard deviations are nothing but the square root of the variances that we have just given up there. The covariance, assume that is equal to minus 86. Now, in this example, we're expressing things in terms of percentage units, not as proportions as we've done before. But that doesn't matter as long as we know what we're talking about. And suppose that with these numbers, we go ahead and we specify the value of the weight on the stock. So we are considering in specific portfolios and something that we can accomplish by just specifying the weight on the stock, because, of course, since the weights need to add up to 1, the weight on the bond will be nothing but 1 minus the weight on the stock. For example, a weight on the stock of 0 will be nothing but a full investment in the bond. And it shouldn't surprise us that the expected return and the standard deviation of this portfolio is nothing but the expected return and the standard deviation of the bond. Also, we could consider a portfolio that invests 50% of our wealth in each one of these two financial assets. In that case, we would obtain, with the numbers that we have in this example, that the expected return of this portfolio is 11.50 and the standard deviation is 12.72. We could also consider positions that imply short selling one of the financial assets. For example, we could specify the weight of the stock as equal to minus 0.10. This implies that we're going to invest on the bond our initial wealth plus 10%. This 10% is financed by short selling the stock. One such portfolio would have an expected return and standard deviation of 8.50 and 17.03 respectively. We could do something similar, but in this case we could specify the weight on the stock as 1.10. In this case, we'll be investing in the stock not only our entire financial wealth, but also 10% more. How do we obtain this extra 10%? We do that by selling the bond. Now, note that it's not necessary to own these assets to sell them. In financial markets, in many financial markets, it is possible to sell a financial asset that you don't own. This is known as a short sale. We can do that, and when we do that, we need to borrow the particular financial asset from somebody else. Then we go ahead and sell it, and at some point in the future, we have to buy it back to return it to its original owner. Now, we can continue specifying values of the weight on the stock and obtain more pairs of expected return and standard deviation. And then we can go ahead and plot in a graph all these values. A graph that has in its vertical axis the expected return and its horizontal axis the standard deviation. Now, for example, the point in the portfolio that considers a full investment in the bond, that is a weight on the stock equal exactly to 0, would be right there, and a full investment in the stock would go right there. In this case, the weight on the stock would be exactly equal to 1. But we can also consider any other point that comes from specifying all possible values of the weight on the stock. If we do that and we plot them, turns out that the whole thing would look like something like this curve right here. Now, it is important to note that that area right there is the result of portfolios that use in the stock more than the initial financial wealth. That is, they short sell, and any point that sits on that area is the result of a portfolio that short sells the bond and invests in the stock an amount larger than the initial financial wealth. A similar thing we can say about points in that area. In that case, what we have is that we invest in the bond more than our initial wealth, and we finance those extra investments in the bond by short selling the stock. Another important point is the one that in our particular example is actually obtained by investing in the stock an amount, a proportion equal to 0.31. This portfolio then has an expected return of 10.55 and a standard deviation of 11.19. And it sits, and let's call it A, just to label it in the graph. And it turns out that it's going to sit right there. Now, why is this particular portfolio interesting? Well, the first reason is because it happens to be, and this can be noticed by just looking at the graph, the portfolio which has the lowest variance of any portfolio that can be built with this bond and this stock. But there is another reason why this portfolio is important. And to give the argument, let's go as follows. Consider, for example, a full investment in the bond. That will put us on the point labeled with B. But suppose that we compare this portfolio with another portfolio that invests a little bit less in the bond and a little in the stock. Rather than full investment in the bond, we're considering almost a full investment in the bond, and that tiny bit that is not invested in the bond is invested in the stock, of course. That would put us in a point like, for example, C. But note what has just happened. If we sit on C, we enjoy a larger expected return and a lower standard deviation. Hence, any rational investor would always prefer C over B. However, we can continue with this reasoning, and we can say, okay, why don't we consider another portfolio that invests in the bond and even a smaller amount, just reduce it by a bit, and that bit is transferred to the stock. In this case, we would sit on a point like, for example, D. Now, once again, we can establish a comparison between D and C, and we can say the same. We can reason in a similar way. No rational investor would prefer C over D. Or, in other words, all rational investors would prefer D over C. How long can we continue with this reasoning? Well, exactly up to A, up to the portfolio that has the lowest variance of all. Now, any other portfolio that sits above A cannot be subject to this line of reasoning. From A on, we cannot improve in an unambiguous way, as we have done so far, by reducing our investment in the bond. Hence, we can say that all portfolios in this region are inefficient. No rational investor would choose them. And all investments in that region are potentially the choice of a rational investor. And hence they're called efficient portfolios. Of course, the actual portfolio, the actual choice of a given investor depends on his of her taste in the trade-off between reward and risk. So we have derived a set that in finance is usually known as the efficient frontier. And this set contains all those portfolios which are above the minimum variance portfolio. That is the efficient frontier. Now, let's consider now adding a risk-free asset to the mix. This may seem a bit more complicated. We are, after all, now considering 3 assets instead of 2. But we can actually look at it as a portfolio of the risk-free asset and a portfolio of 2 risky assets. That is, we can somehow look at it as a portfolio of 2 assets only. One of them would be the risky asset, and the other one will itself be a portfolio of 2 risky assets. Now, if we look at it this way, we can go ahead and use our useful tool, the capital allocation line, and analyze what would happen. What we're going to do now is that we will actually see how we can derive the efficient frontier when we have now 3 assets. 3 assets of this type, 1 risk-free asset and 2 risky assets. Now, and we're going to illustrate this with our example once again, and assume that in this example, this asset that we have just added has a return of 6%. In other words, the risk-free rate is 6%. So we depart from this point, right? We have that, okay, we consider portfolios of the 2 risky assets and we want to add a risk-free asset. So we could just create a portfolio of the risk-free asset and another portfolio of the 2 risky assets. For example, we can consider a trivial portfolio, which is just a full investment in the stock, and mix it with a risk-free asset. We know that any portfolio such that will sit on the capital allocation line of the stock. But we could also consider an investment, a portfolio of the risk-free asset, and for example, portfolio A, the portfolio with the lowest variance of all. And then any portfolio like this will have to sit on the capital allocation line of A. But now let's make an important point here. Note that we could consider a point sitting on the capital allocation line of the stock and compare it with another point sitting on the capital allocation line of A. That particular point on the capital allocation line of A clearly dominates the other point. So because it has an expected return that is higher than the point on the capital allocation line of S, and it has exactly the same standard deviation. If we extend this reasoning to any point on the capital allocation line of S, since we can find another point on the capital allocation line of A that dominates any point, any such point, we can conclude that no rational investor would actually choose a point sitting on the capital allocation line of S. They would rather choose a portfolio on the capital allocation line of A. And note that this applies to anything that is below the capital allocation line of A, including those points sitting on the blue line below the capital allocation line of A. But we can continue pushing further up capital allocation lines, the capital allocation line, finding capital allocation lines that are actually steeper by judiciously choosing a portfolio on the blue line. We can continue moving that way, but we need to stop somewhere. How far can we go? And the answer is right there. That's the steepest capital allocation line, which will correspond to a portfolio of the two risky assets and the risk-free asset. Our capital allocation line gives us the portfolios of the risk-free asset and a portfolio of two risky assets, which sits exactly at the tangent of the efficient frontier with two risky assets only and the capital allocation line of such portfolio. Now, we have used a T on purpose because that particular portfolio we have just found, which sits at that tangent, that is, its capital allocation line sits at the tangent with the efficient frontier, two risky assets only, is known as the tangency portfolio. It is the portfolio of risky assets whose capital allocation line is tangent to the efficient set of risky portfolios. And note that when we add to the mix a risk-free asset, now the efficient frontier is not the blue line anymore. Now the efficient frontier is exactly this capital allocation line. Anything that sits below that is going to be disregarded by any rational investor. Now, note that since the slope of the capital allocation line happens to be the Sharpe ratio of the associated portfolio of risky assets, or the risky asset that the capital allocation line uses to build it, then since the tangency portfolio has the capital allocation line that is the steepest one of all the capital allocation lines that can be built by using the portfolios of risky assets on the blue line, on the efficient frontier of two risky assets only, it happens that, as it turns out, this capital allocation line, the tangency portfolio, is also the one that maximizes the Sharpe ratio. That is, this tangency portfolio gives us the maximum value of the Sharpe ratio that can be attained by mixing those three acids. So that's the graphical illustration of what we have just derived for the case of three acids when one of them is risk-free. Now, we're going to conclude by taking a last look at the expression of the variance of two risky acids and checking what the effect of the co-movement between the two risky acids is on the variance of any portfolio of those two risky acids. So if you remember, that was the expression of the standard deviation of the portfolio of these two risky acids that we're looking at. And I want you to focus now on the covariance, because we can do something with it. Since the correlation is equal to the covariance divided by the product of the standard deviations, we can actually use that definition to write the covariance in terms of the correlation. We factor out the covariance and then we write it as the product of these two standard deviations times the correlation. So we can go ahead and plug into the expression of the covariance the corresponding expression that we have obtained that is written in terms of the correlation. That is, we go and plug into there that, and we obtain the variance of the portfolio of two risky assets in this way. Now, note that the correlation is a value that is between -1 and 1. This implies that the variance of the portfolio for given values of the standard deviations of the elements of this portfolio will actually be the lowest the closest we are to -1 for the value of the correlation. So it will be a decreasing function of the value of the correlation. That is, the maximum inverse movement, we can say, between the two returns, the lowest will be the variance of the portfolio for given values of their standard deviations. Maybe it would be much better to see this with an example. So suppose that we have our previous numbers. We just bring back the example and we have used before, but now we focus on the correlation. And we can use the expression in terms of the correlation to compute the standard deviation of any portfolio of these two acids. Of course, we have assumed a value of the correlation of -0.2372, but we could have assumed any other value of the correlation in this example. This is just an example. So, for example, what would happen if we had chosen a value of the correlation instead of 1? Let's see how our graph would look like. First, note that the expected return is not going to be affected at all by this change, because the expected return of the portfolio does not depend at all on this correlation. Now, we choose a correlation of 1.0. We assume that the correlation between these two assets is, the return of these two assets is equal to 1.0. Then, what we get is not a curve anymore. We actually get a straight line. And the important point here is that by building portfolios of the returns of the two risky assets, rather than going full investment in each one of them, and in the bond, for example, we're actually not getting any diversification gains as we did before. That is, we're not going to get that effect that we discussed where we could actually decrease the variance and increase the expected return by reducing our investment in the bond. In other words, in this case, the curve, there is not the points linking the line giving us the pairs of expected return and standard deviation is not a curve that bends to the left. However, this is a extreme case, and in reality is hardly ever the case. We could have lower correlations instead. Suppose that rather than 1.0, that instead of 1.0, we assume a correlation of 0.8. In that case, things improve a bit. The standard deviation is not anymore a weighted sum of the standard deviations of the bond and the stock. It's not a straight line anymore. And we can somehow, we're not going to get that pattern that we got before. We don't get either any sort of bending to the left that would allow us for clear diversification gains that as the ones that we have depicted before. But if we lower the correlation a bit more, things start looking a little bit better. And if we do it even further, for example, we lowered it to 0, we start getting that clear bending to the left, where we see that a full investment in the bond is clearly inefficient, and where we can actually establish clearly a distinction between the efficient part of the curve and the inefficient part of it. Now, we could have even considered or assumed an even lower correlation, for example, minus 0.5. In this case, the bending is actually bigger, and then we can obtain a larger diversification gains by going for the portfolio rather than going for full investments in each one of these two risky assets. Now, the most extreme case is the one that we obtain when we consider instead, or we assume, a correlation of -1. This, once again, is hardly the case in reality. But what we obtain in that case, what happens in that case is that we can actually reduce the variance down to 0. So we can, by judiciously choosing the weight on the stock, the weights of this portfolio, we can actually find a portfolio whose variance is exactly 0. That is, a portfolio of these two assets, there will be one portfolio of these two assets, which in effect will be a risk-free asset. And we can see then, with this series of graphs, that the value of the correlation between two risky assets that we are considering is going to set the value of the diversification gains that can actually be accomplished by building portfolios of the two elements of it. And this is where we're going to stop here and stay tuned for the fourth video on the series on portfolio theory.